Hello everybody, welcome to today's Noveg webinar, Simulate any mix of geometry with Intact.Simulation for Rhino and Grasshopper. Intact.Simulation allows user to tackle the most complex geometries without hurdles. And as you'll see in a few minutes, Intact.Simulation performs this task using mixed geometry, flexibility, and increased performance and accuracy. Today's webinar presenter, Michael Freitag, is a founder and the Director of Development at Intact Solutions. He's also an experienced designer and craftsman who is passionate about bringing life to conceptual designs, physically and virtually. He holds a PhD in mechanical engineering and a master's degree in computer science from the University of Wisconsin-Madison. And now let me tell you a little bit about Noveg and what we do. Noveg is changing the way designers purchase 3D software. How so? We offer a lot of choices and the freedom to select different product, compatible or not, and you get the best advice because you can call us anytime. Check us out at noveg.com. And now I will switch my screen to let Michael present. Just a second. Michael, let me know, okay, if you get the prompt to share your screen. Okay, we can see your screen. Take it away, Michael.
Okay, excellent. Thank you for the kind introduction. And thank you for the attendance of everybody that's in attendance today. My name is Michael Freitag. As Barbara mentioned, I'm the Director of Development for Intact Solutions, and I'm pleased to present Intact.Simulation for Rhino Grasshopper today. This is our latest product offering. It builds on a long history of research and development that we've been doing over several years. So it's nice to have it finally out and available. So let me I'll tell you a little bit about the company. Intact Solutions was founded in 1999. It's a spin-off from the University of Wisconsin-Madison in the mechanical engineering department. We've always had a focus on automating simulation, primarily for designers and engineers to aid their conceptual design process and to help them, throughout their design workflow. We have a long history of innovative R&D, where we do a lot of industrial and government-funded research, primarily in the simulation domain. And then we turn this into products that are available for consumers to use. Some of our earliest stuff we've got is Field Magic, which is early 2000s era, which is a very simple interface for a very simple simulation tool for doing 2D simulation on 2D models. In 2011, we released Scan and Solve after several years of research in the labs at the university. In Scan and Solve for Rhino, we released version 1 in 2011, and over the years we've added functionality as we performed research projects, either government or industrial funded. Now, throughout this process, in 2016, we released Intact Design, which is an online web tool for simulation for use by makers. It has a very simplified interface, but it works with Onshape as well as STL models that are uploaded to the cloud. After several more years of government-funded research from DARPA and as well as industrial partners such as Xerox PARC, we've produced the new Immersive Method of Moments for doing simulation on using meshes that do not conform to the geometry. With this method, I'll go into a little bit of detail later, but it completely eliminates all of the meshing bottlenecks that you typically incur when you're working with simulation. With that technology, we've produced a product called Intact.Simulation, which is a simulation toolkit that is mesh-free in that the meshes do not have to conform to the geometry. It supports any geometric representation that is unambiguous. It does solids, meshes, G-code. It supports any material model, isotropic, anisotropic, composites, you name it, it supports it. It also supports a wide range of physics. We're only going to be demonstrating 3 physics today, but if that functionality, if additional functionality is required, we can, please talk to us. The Intact.Simulation is available as a C++ API, a Python API, as well as the functionality is also available through the command line as an executable. And today, I'm going to be demonstrating Intact.Simulation, which is actually a front end for the command line version of Intact.Simulation. So Intact.Simulation for Rhino Grasshopper, that's what I'm going to be talking about today. So everybody probably that's attending this knows why do we do simulation, but I think it bears repeating that the idea of simulation is that we want to predict product performance early in the design process. So here I've got the sort of the design process laid out. We start with a conceptual design, and from the conceptual design, we work on the detailed design, defining what the shapes are that we're going to be creating and how they're going to fit together. Once we're done with the detailed design, we build a prototype. From the prototype, we do some testing, and if everything goes well, we send it on to production. Now, 70 to 80% of product cost is determined at the design stage, long before prototyping and testing. So it's useful to have tools available at that stage where you can make design decisions, choose from alternative designs, identify and avoid design mistakes early in the process where they're relatively inexpensive to fix, because you don't want to go through testing and have to go through, start the process again from conceptual design when you discover an error during testing. Or the worst case of all, if you end up going to production and you've got a problem that is now you have to do a field service or you have to do a recall on your product. So traditionally, simulation uses body-fitted meshes. So we're talking finite element analysis, where the finite element mesh is actually becomes a representation of the geometry. So we have a body-fitted mesh where the mesh has to basically fit to the geometry of the shape. This process of creating a mesh is extremely messy. It's typically very manual. It's also very costly. It's around 60 to 70% of the simulation process is actually in data preparation to be able to create a mesh, removing fillets, removing errors in the geometry, things like that. With Intact.Simulation, all of those problems go away. So how do we do this? With the Immersive Method of Moments. It's finite element analysis without the pre-processing and the meshing bottlenecks. We operate on the native geometry by immersing the geometry, the native geometry into a background analysis grid, which is it is a finite element analysis grid. But instead of fitting that analysis grid to the geometry, we do computations over the native geometry and then build a mathematical model in the mesh of the analysis grid that gives us the simulation results that we're looking for. By eliminating meshing, we empower automation, so you can apply simulation within your workflow automatically without going through the process of creating meshes or simplifying your geometry and doing those pre-processing tasks. The method has been benchmarked, it's been validated, it's been tested, it's been published. We have publications available for those that are interested. So I guess I'll ask here if there's any questions. I'm not seeing any at the moment, but if they do come up, please type them into the chat. I'm not sure if I see the chat, but if they do, I'll try to address them. So with that said, I'm gonna move into the demos. I'm going to cover the basics of the types of simulation that Intact.Simulation for Grasshopper actually supports. We'll start with a stress simulation, and then move on to a thermal simulation, and then a modal simulation. And then throughout this, I'll try to talk about a little bit of the more advanced topics that are important during simulation, like units, custom materials, solver settings, and then some peculiarities of displacement conditions, and then also leveraging the capabilities of Grasshopper to empower automation and simulation. So the first simulation, or first demo, I'm going to do is a stress simulation on a relatively simple geometry. we call it, it's a link. We'll talk about the settings, setting up components, setting up restraints, setting up surface loads, in this case, a bearing load, and then visualization of results. So switching over to Rhino. So this just gives you a taste of what we're going for here. On the right, we see simulation results already, but I'm going to show you how we actually set this up. So I'm going to delete everything in my canvas here. And we start from scratch. Actually, I would start with a different model than this one. Turn this one here. So what we want to do is actually apply loads, do a simulation on this shape. What we've got is we're going to fix the inside of this cylindrical surface here and apply bearing load that pulls this, attempts to pull this link apart. To do this, we look at the Intact, we go to Grasshopper in the Intact.Simulation menu. Here we see our solvers. We got a variety of solvers available. We have components and materials, restraints and loads for structural problems, as well as boundary conditions for thermal simulations. Then we'll get into the results and the other I/O things as we go along. So to set up a stress simulation, we choose the stress simulation block and add it to the canvas. Now, working top to bottom, we specify solver settings, components, restraints, loads, surface loads, and volumetric loads. The first thing we'll do is add the simulation settings. That is this tool right here in the solvers block, which is a little gear icon which has the basic solver settings in it. By default, it's set to a resolution of 100,000 elements, which is perfect for this particular geometry. It's enough to give us decent results. So after that's inserted, we'll just use the default settings. It's good enough for what we're doing right now. So plug that in, we're good, that's set. Now, what we want to do is specify the components that are going to participate in the simulation. To do that, we go to the components and materials block of the Intact.Simulation toolbar, and we add a simulation component. A simulation component takes a geometry and a material. There's an optional input here, which we will ignore for now. So for the geometry, what we want to do is reference this solid in Rhino. In Grasshopper, what we do is we specify a BREP in Grasshopper. This BREP block will reference this geometry here. So to make that reference, we right-click on the BREP block and say set one BREP. The context immediately switches to Rhino, where we can select that solid. And now the context is gone, so we've gone back to Grasshopper. So now we've got the BREP specified, and we plug that into the geometry input. So we're halfway there. We need to specify now a material. For this, we'll just use a standard material. So we go to the Intact.Simulation menu and choose a standard material block, and we add it to the canvas. Now we see here that the material block is actually red, and that's because I have to select a material. The help button actually says, right click on the block to select a material. Right click on the block, and for this I'm going to choose a gray cast iron. But there's a wide variety of different materials available, from 3D printed plastics to engineering plastics and non-metals. But for this, I'm just going to choose a gray cast iron. So that material has been selected, and we just want to input that into the component, and our component has been fully specified. I plug that into the components input on the stress solver, and we see that it's turned red. And looking at the help button, we see that we need to specify loads, and we need to specify restraints or displacement boundary conditions. So we'll start with specifying restraints. What we're going to do is we're going to be restraining this surface here. So to do that, I will input a fixed restraint block. Choose that from the menu, add it to the canvas. The geometry of the restraint on this end is a surface. So I add a surface to the Grasshopper canvas by double clicking on the canvas and choosing surface. And by right clicking on that surface, I can set one surface. It's now referenced. I plug it into the restraint. And from the restraint block, I plug the restraint block into the solver block. Now, we need to specify our loads. Our loads, as I said, we're going to be basically a bearing load pulling to the left on this shape. A bearing load is specified using a bearing load block. We go to the menu, select the bearing load block, add it to the canvas, and the geometry is going to be, again, a surface. Right click on that, and we're going to set multiple surfaces. We're going to drag and click and drag, and we've now selected these surfaces. And we're going to, hit return when those are selected. And I plug those into the geometry of my bearing block. Now, a bearing load involves geometry of a direction as well as a magnitude. The direction in the case of a bearing block or bearing load is a vector. So we double click on the canvas and specify a vector. This is a vector. And again, we right click and set one vector. By default, the tail of the vector is at the origin, but I want a different tail. So I will choose a different start point for that vector. And I choose the center of this hole. And we're going to point it toward the center of this hole. So that vector has been specified. We plug it in. And now we just need a magnitude. I will specify the magnitude by, again, double clicking on the canvas and entering the magnitude. It shows up as a number slider, so we could change it, but I'll just leave it 300,000. So our bearing load has been completely specified. We have the geometry, a vector direction, and the magnitude. We plug this into the stress solver, and we can see a preview of how those boundary conditions are going to be applied. We've got a restraint over here, and we've got the bearing load applied here. I'm ready to solve. I'm a little out of date because we're constantly updating the software. My version's a little behind, but it still works. It's ready to go, so I hit solve. It goes off, starts the command line utility, just the command line solver, runs it in about, I guess, less than 10 seconds. We have simulation results. To visualize those results, we go to the toolbar and grab the visualize block. And the visualize block takes, a visualizer block takes through 4 inputs, which the first one is a simulation of some sort, whether it's modal stress, like in our case. I apologize for that. That's my emergency test. It's occurring everywhere.
I guess we're all hearing it.
We're all participating today.
That's the beauty of being live. Now you know we're not,
right.
leading you.
Okay, so back to this. So the visualization tool takes the stress solution, and it's basically ready to go. If we check the help bubble, it just says, right click to select the solution quantity. Right clicking, we select the solution quantity, and we see a bunch of different options are available here. We've got displacements, we've got strains, we've got stresses, we got danger level, we've got topological sensitivity, all available. So I'm just going to choose, we'll just do danger level for this. And this on the right, you see the danger level display, or the danger level being displayed on the geometry. And what we've also got is, it's just an artifact of Grasshopper and Z. We've got some Z fighting going on. So I'm going to turn off the display of the Grasshopper display of the geometry that is participating in the simulation. And I'll also switch to a wireframe view. So now we can see the results here. Now this danger level, I think if we add a panel, by double clicking adding a panel, if I'm doing this right, we'll see that the danger level actually exceeds 1. So we're actually 6% higher than the yield strength of the material. So we're in danger of this thing potentially breaking. So what do we do about that? We can easily with Intact.Simulation for Rhino Grasshopper, we can easily switch out the geometry and save the existing boundary conditions and apply them to a new shape. So I've already got a new shape defined, and it is this blue shape. I'm going to turn this off here so you can see. Turn off this. Sorry, my preview is not there. So this is a different shape that we will use to specify that we want to simulate on, and we'll reuse the boundary conditions that we applied to the original shape. To do that, I'm just going to go over here to the BREP input and set a different BREP. So set one BREP. I'll set it to this BREP, and now it's set to that BREP, so we can actually solve again and see what the solution, what the results look like. Give it a second to run here. Switch to a wireframe view and turn on the preview of the results. And here we can see that our danger level has been reduced to less than 1. But so basically, we're not going to fail at this particular loading, but we're pretty darn close. So what can we do? We could try changing the material. That's a simple, easy thing to do. We go over here, on the material block, we can choose a different material from the selection options. I'll just go to a 1018 steel. I'll choose that one. Now it's ready to solve again. I can see what happens with that. So I choose solve. And we've got new results using the new material. Now, you can see here the danger level has been reduced to 0.38. So it's been reduced by about 60% just by choosing that better material. And we could probably use the original design using this material as well. But in this particular case, this geometry is actually smaller, has less volume, so it actually uses less material. So there's a couple other options we can play with here while we're looking at while we're visualizing the results. The deflections, there's a deflection input, so we can actually get a preview or a zoomed in model, zoomed in view of what the geometry looks like when it's being loaded. So what we'll do is specify a magnification factor for that by double clicking on the canvas and entering a slider. We'll plug this slider into the deformation input, and we get a magnified view of what the deformation looks like. And the slider, we can do this interactively. We can see how the shape, exaggerates. It's at this scale, it's 1,000 times what we specified, or what the actual simulation results are. We can also look at different quantities. We have this, like I said, displacement. So here's the total displacement display. We can also look at the von Mises stress. We can also look at topological sensitivity, which gives an indication of where we would probably want to add material, or where the simulation is telling us we should probably add material, which in this case we can't really do, so we have to try something else. And we can also do strains and principal stresses. At this point, does anybody have any questions?
No questions so far. Everything
no
is
questions.
Clear. Yeah.
Everything is clear as mud. Okay, good to go. So let's switch back to the presentation. So I've covered surface loads. I've covered bearing loads, but we also support vector loads, displacement conditions, pressures, and torques. And we also support body loads, so gravity, linear acceleration, and rotational acceleration. And those are also available through the interface. Where is it? Oh, it's here. So here we've got the bearing loads. I showed bearing loads, restraints. Here's the linear acceleration option, load option, rotational load option, a vector load, displacement boundary conditions, where we can specify how particular faces are displaced in particular directions, whether it's 0 or a particular specific displacement amount. There's a gravity load, We also have pressure loads and torque loads. And moving on to the next one, if there are no questions. We also do thermal simulation. So in this example, I'm going to demonstrate how to do thermal simulation with the solver, with the thermal components, including convective and heat flux boundary conditions. And this example also brings in the power of Grasshopper for doing parametric design changes, and we'll demonstrate how to do simulation after these parametric design changes take place. So switching over to Rhino Grasshopper again. On the left here, we've got a Grasshopper definition that is constructing, in purple, it's constructing this geometry, which is a notional heat sink that has, say, there's a heat source at the bottom here, say maybe a CPU or something that's generating a heat flux that we need to dissipate into the surrounding air. What's parameterized in this model through this Grasshopper network is the number of fins. So the fins are just controlled by this slider. So at each one of these slider settings, we get a different geometry. So in this case, we've got five fins, and Grasshopper is constructing a solid that we'll then use for analysis downstream. The solid is input into a component block that we've already seen. And in this case, I'm specifying a material that's a thermal material. Thermal materials are available, again, in the components and materials section of the toolbar. So we select one of those, and by right-clicking on that, we can select from a variety of available standard materials that have thermal properties available. In this case, I've already chosen an aluminum, I believe. Yeah, so this is a 6061 aluminum. So this heatsink is made out of aluminum. It's got 5 fins, and we plug that in. We create a component that combines that geometry with 5 fins with an aluminum material and plugged into a thermal solver, which obviously comes from up here. Now, for this heatsink, it's in an environment where it's in ambient air. So the environment temperature is in Kelvin. So this is 20 degrees C. So 293 corresponds to 20 degrees C. And we're using a convective boundary condition. The convective boundary condition consists of geometry where we've got where the heat is being dissipated into an environment, a coefficient of the heat transfer to that fluid environment, as well as the temperature of that environment. Like I said, the temperature of the environment is 293 Kelvin. Our coefficient is 39 watts per square meter per degree Kelvin. And our geometry is the entire surface of this shape. Because we've got a heat source on this, we've got a heat source on the bottom here, which is represented by this, or is being imposed by this square. That involves a heat flux boundary condition. So we specified that. Sorry, let me preview that. So this geometry, we've got a heat flux applied over this square area that is incorporated into the heat flux boundary condition. And the heat flux has a surface as well as a heat flux coefficient, or a rate of heat flux. And here I'm doing a little bit of math in Grasshopper. So I'm taking my 250 watts of heat dissipation, say from a computer chip that's generating 250 watts of heat, and I need to convert that into a heat flux. So I want 250 watts being applied to this area. So I'm taking that 250 watts and dividing it by the surface area of this square area, of this square interface. I do a little bit of math here with Grasshopper, do a division, and that becomes a heat flux into the shape. Now, in this case, I'm adding two components at the same time, or two inputs in here. For those that aren't familiar with how Grasshopper works, normally you would insert a merge component. So you would do this. So you can combine these two boundary conditions into one to dump them into the solver for the simulation. But you can also do if you do a shift, you can bypass that and just add two components to the same input at the same time. It does the same thing, it merges them. So everything is ready to go. I've already specified the default resolution of 100,000. My components are set up, my boundary conditions are set up, and I'm ready to solve. So I choose solve. Grasshopper my plugin sends this out. We got a result, and we just need to turn on the preview to see what it looks like. Just disable this and turn off this layer. So here is the temperature distribution for a 250 watt heat flux using this environment temperature and coefficients of heat transfer for convection. Now, this temperature, this maximum temperature of 665 is probably too high. So what can we do? We can increase the number of fins. And I do that by just increasing the fin count over here with the slider. And we can see what happens if I increase it to, say, 35. Now I've got this new geometry with 35 fins, and I can solve this again. And we see that our temperature has actually gone down from 360 to 400 degrees, which may be more manageable. And if that's not enough, we can increase the fin count maybe even more. It's easy to do this, within this Grasshopper workflow, to easily try different designs by simply, modify the geometry using Grasshopper and then run the simulation again. So we went to, I guess I lost track of where we were, but it's going down, believe me. We're adding fins, it's going down. Does anybody have any questions at this point?
Still no question, but it's a good reminder that this is, this is your chance.
Okay, yeah. Please weigh in if you have questions. So that's thermal simulation. And then one more thing we'll do is modal simulation. We also support modal simulation. And with this example, I'm going to demonstrate modal simulation as well as a mix of geometry types. This mixes three different types of geometry, and one of the geometries is particularly complex. So that's what's particularly interesting about this example. Sorry. lost my thing. Switching to that bracket model. This workflow is for a NASA, I guess, a standard sort of a challenge problem. This is the input here is a surface mesh that is then fed through a variety of other tools to create an implicit model of the geometry that we can use for simulation. In this part of the workflow, we're constructing an implicit representation of the outside shell of this shape, as well as an implicit representation of an infill that's a dodecahedron lattice. So these are all represented implicitly by an implicit by an implicit representation, in this case constructed by a tool called Dendro. And we'll take this Dendro output as a VDB model, which is a file format for representing volumetric surface, sort of like level set data. That is a nice lightweight representation for complicated shapes like we are experimenting with here. So from Dendro output, we dump it into a Dendro, a VDB file. Our solver Intact.Simulation has a VDB reader. So what I do is incorporate a read volume block, which has a reference to an external file, as well as a toggle to read that external file, which is what's happening actually right here. This geometry gets output as a VDB, and we read it in and use it for simulation. So this is VDB geometry. This geometry also incorporates 4 meshes. So there's interfaces between this VDB geometry, this complicated VDB geometry with the lattice infill, and these interfaces, which are actually surface meshes. We combine these surface meshes with the VDB geometry, and we create basically a list of components using a material that is fed into our component block. Now, what we're going to do is feed these into our modal simulation. But before that, this is actually is doing something useful for a rocket ship or something. So we've got a solid up here that represents a cargo that's being supported by this bracket. And to do this, to represent this cargo, we've actually got a boundary representation, which is a Rhino poly surface. And because the geometry has a particular shape, or sorry, the cargo has a particular shape, which we don't actually have access to, the only information we have is we know its center of gravity and what its mass is. So here we're using a little bit of Grasshopper mathematics to actually compute a density for a custom material that we can apply for this component, to apply to this component in green in a modal simulation. So which introduces the idea that we can actually have custom materials, which are available right here. So these are custom ductile materials and custom brittle materials, where you can specify each of the components or each of the material properties individually. In this case, I'm using the same properties as I'm using down here for this material. I'm just overriding the density so that I have the mass properties that I'm looking for. So I've got the cargo component here, and I've got the bracket component, and we're going to just basically combine these together and feed them into simulation so that we've got 5 components participating, 6, 5, 6, 5, 5 components, I think, participating, a boundary representation, a VDB model, as well as 4 surface meshes. Again, we're going to use the standards, the default solution settings for our modal solver. Our restraint is a little bit interesting because it's just a surface at the bottom, which is where this surface is contacting the bottom of the geometry. These surfaces will be restrained and fixed. And we're specifying that we want 5 frequencies out of our modal simulation. So if I go and click solve here, it's going to go off and compute the 5 the 5 lowest frequencies of natural frequencies of vibration for this assembly, and give us those results in a few seconds here. Takes a little bit longer here because it's writing the outputs for an assembly, which basically for 5 frequencies, I think there's 5 or 6 components. So I've got multiple files that are being generated and parsed in here. So our solution is now ready. And if I turn on the preview, I can actually see what those mode shapes look like. Now I've got a little bit of interference here because I've got the existing components turned on. We'll just turn those off and turn off this one as well, turn off the preview. And we can see here what this is the first mode, first vibration mode. And our available modes are mode 2. We've got, I believe I specified 5. So that's mode 2. mode 3, mode 4, we'll do mode 4. So all of these mode shapes are available. Mode 5. And this is all done within, within Grasshopper and with a variety of geometric representations, which typically you would have to construct meshes that conform to the geometry. With our system, we don't have to do that. So it's obviously very seamless. So like I mentioned in this one, we have VDB.io. We also demonstrate with this example that we can leverage Grasshopper functionality to do some mathematics and combine that with our inputs for simulation. And I also demonstrate how we interface with other tools. So we've got the Dendro, which is creating an implicit representation of the sculpted shape, which we're then using directly in our simulation. Now I've got a final example here, which is just sort of a toy problem that I've been working on in my spare time, which is a fully parameterized staircase that will basically, by moving things around, you can construct different staircases and do simulation according to some inputs from like the building code. So if I switch over to Rhino and Grasshopper here, you can see it gets a complicated workflow. Most of this is just generating the geometry for the staircase, but some of the inputs are the number of steps, so I can increase or decrease the number of steps. Increase the number of steps. 6 is probably not enough, a little bit too far apart, but it does what it needs to do to fill the space between the geometry, between the what do I call these? Between the landings. So if I move this geometry, everything updates. But I've already got a solution already. There's a solution actually sitting here, so it's a little convoluted, but a little confusing. But what I'm doing here is this is probably too complicated. But I'm using the Grasshopper functionality to actually select which parts of the geometry I'm applying boundary conditions to. I'm converting these brackets to surface meshes and then selecting the upper surfaces. I think I might have actually broken it. I'm gonna kill this. Hold on a second. I think yeah, front view, top view. Yeah, I moved the geometry into a position where it doesn't actually work. I'll try this. And I'll run the simulation again. I think this one actually will work. So in this case, what it's doing is actually going through and it's taking these riser brackets, converting them to surface meshes, and identifying the upper faces so that I can distribute a load over those faces corresponding to 100 pounds per square foot of pressure per step. And then it's applied over each of these steps. That occurs within this section of Grasshopper here. We can also use a similar technique to grab the top surfaces, the top of the middle step here, where I've got a 600-pound load applied just to the top surface by selecting the top faces of that surface mesh. And those are fed into boundary conditions and fed into my stress solver. And we can see here those results for that set of conditions. If there's still no questions, I will go back to the presentation. Oops.
Yes, no question. Everybody's either very shy or very knowledgeable. So.
Okay. Yeah, I'm probably covering stuff that maybe the Grasshopper users probably are saying I'm doing this completely wrong, but it works. So if there are no questions, I'll move on. So at this point, I mean, this is sort of the end of the presentation, I encourage you to try Intact.Simulation for Rhino Grasshopper. Here's links to download the trial. It goes to our website. You can download the trial from there. There's links to the documentation. And looks like that link is actually broken at the moment, but I can fix that easily enough. We also have examples. Yep, that one's broken as well. Sorry. They will be working by the time this webinar is published. So if nobody has any questions, I guess that concludes the webinar.
Thank you. Thank you so much, Michael. That was exciting, and I urge everybody to download it and test it out. That's
And please,
certainly
if
the
you have
way
any
to.
questions, please reach out with, just to our Intact Solution support email if you have any questions that maybe went unanswered today.
Great. Thank you so much, Michael. I will take the screen back, and I want to show everybody where they can get Rhino before they download Intact.Simulation. Just go to noveg.com, and Noveg is changing the way designers purchase 3D software. As you know, we have all the choices and the freedom to buy different software from different brands, and get them all into one cart. You can call us anytime also for any problems with subscriptions, renewals. We're here for you. Thanks again, Michael. That was very interesting and exciting. Please test Intact simulations, everybody, and let us know. Have a great day, everybody, and see you at the next webinar.